She's a renowned expert in NMR, ESR, coherent control, and quantum information science, and a specialist in sort of spin-based quantum information processing and precision measurements in solid-state systems. And she's going to present a talk today. You already see the title, Quantum Enhanced Sensing. So Paola, thank you for attending, and we look forward very much to your talk.
Thank you very much for the very nice and generous introduction, and thanks everybody and the organizer for putting up this conference in this very unusual way, but also very, very effective. So what I'm going to try to do today is to try to explain how we use quantum properties to enhance sensing. And before I go ahead and do this, I'd like to sort of review a little bit what we mean by quantum sensing. And this has actually already been touched upon by the previous speaker, by Hans, who already mentioned this paper that we had together with Professor Degen and Reinhardt a few years back. So there we were sort of asking ourselves the question, how can we define a quantum sensor, but rather than on a very theoretical way, in a practical way, what are devices that we can indeed use as sensors? And our answer was that there are different types of sensor with different levels of complexity and different level with which they use quantum properties to achieve improvement. So the first thing that you can think of is, for example, simply an MRI that many of you potentially have already undergone. So these, of course, exploit a very quantum properties of physics, the spin, but most of its operation can be described by classical means. And so this is, if you want, the simplest way that we can use quantum to indeed try to achieve some sensing. And this is not really what we are interested, at least no longer recently. A lot of the quantum community is more interested in actually trying to exploit at least some properties of quantum mechanics, such as coherence, in order to try to achieve an advantage over classical sensor. And the typical way of trying to do that is actually to exploit quantum entanglement. And so this is really what I would like to focus on today. How can we try to exploit some entanglement, some more advanced properties of quantum physics in order to achieve some improvement in sense. Of course, what are ways that we can exploit entanglement? The simplest way, if you want, is to create an entangled state. And so this is the prototypical example of which I would say I use in my quantum engineering course to explain the advantage that entanglement can bring to sensing. So you create some sort of entangled state, and maybe it is not just a GSE state, but a bit larger, like a cut state. And then if you're trying to pick up, for example, some external field which couples some sort of collecting SZ type of fields, this state will evolve n times faster than a non-entangled state. And so you will acquire a phase which is n times the phase that a single spin and superposition would have acquired. In turn, what this does is a square root of n enhancement in the signal-to-noise ratio when you consider unit time, so a measurement which only happen for one unit of time. Is this actually a very good strategy, or is this just theory? Well, there has been some demonstration of trying to do quantum sensing with GSE state, but we have not really reached, if you want, practicality. It's very difficult to create a large cut state involving many, many spins. However, we can try, and indeed, even in my group, we did try to do that. And for example, we create a GSE state in diamond. So what do we need to do in order to create a GSE state in diamond? So first of all, we identified a single NV centers, and NV center have already been discussed, for example, by Amir, so I'm not gonna really explain much more about them. But here, the interesting fact was that this individual NV center was close by two other spins that I will call dark spin because they do not have any optical property. And so we can see optically the MV centers, but we do not see the other two spins which are nearby. They're still electronic spins. And so we can hope that the MV center couples to them via the magnetic dipole-dipole interaction. So what do we do to reveal the existence of these two spins? And so we perform a spin echo on the MV center, so a pi/2, pi, and a pi/2, and this will decouple the MV center from its environment. However, at the same time, we also apply, at the same time as the pi pulse for the MV, a pi pulse in what we hope is the frequency of some other spins in the environment. And to check out if there are indeed some other spins, we sweep the frequency as shown here of this pulse here. And what we found, quite surprisingly, was that there were actually signatures of two different nearby spins coupled in a coherent way to our MV centers. What was surprising was, if you want, the fact that we were seeing this doublet here. So one is the gray one, and the other one is in blue. And this tells us that these spins are electronic spin, but they're also coupled to a nuclear spin. And actually, we try to look for the very large existing literature on defects in diamond that people have accumulated over the years because they're mainly interested in creating beautiful diamonds by including defects. And we could not really find any report of such similar splitting, or if you want, coupling to their nuclear spin. So these defects are still at the moment sort of unidentified, although we can know that they're quite coherent, they don't have optical property, they're quite stable under laser illumination, and so we can actually start to exploit them. The nice thing about the fact that actually they have very distinct hyperfine transition is that we can focus our microwave resonance driving on one of these transitions and not drive the other one. So we can, for example, drive spin 2, but not spin 1, and vice versa. And this really allows us to have a universal control on this 3-spin system. It's actually, if you want, a 6-spin system, but at the moment we sort of neglect the nuclear spin for simplicity. So using this 3-spin system, what we can do is to create indeed the geodesic state that I showed before, this highly entangled state. And so we can show that it can actually evolve 3 times faster than a single spin coherence. So here we show I show the spectrum of the modulation frequency under this driving, if you want, of the 3-spin system with an external longitudinal field. Actually, what we did was a bit more complicated. We drove each one of the spin at a frequency which was 1, 2, and 5. These are sort of arbitrary units because we actually changed the phase of the driving field instead of adding a real magnetic field. And in any case, we can see that the signal that we observe is at 8, which is indeed the sum of these 1, 2, 3, 1, 2, and 5 modulation frequency that we have. So we can indeed demonstrate that we can create this highly entangled state using 3 spins in diamond. But can we use it to actually do sensing? And can we use to do sensing in a way which is better than just using, let's say, only the MV center and neglecting that there are 2 other spins nearby? So this is a slightly more complicated question. And so the problem is that every time that indeed you have this nice entangled state, yes, you acquire a phase which is n times faster than for a single spin, but this phase might also come from noise. And so you can expect that also your coherence time will be n times shorter because the same type of phase enhancement also applies to the noise. Also, there are other things like very large overheads due to the fact that you need to initialize your state in this entangled state, and also the control of the entangled state and the readout may be a bit more difficult. So this is just, for an example, is the sequence that we use to first initialize our MV and the other 2 electronic spins, and then entangle, perform the sensing, and then decode before measuring out the MV center, since we cannot directly measure the other 2. As a matter of fact, this is what it looks like. because each one of the spins has two transition lines which are far apart from each other, but we cannot control them at the same time with very high fidelity. So we actually sort of perform the control in sequence. So what do we need to do? Well, the MV can be initialized, polarized optically, but the other two node are in a highly thermal state. And so first we need to transfer the polarization from the MV to the other two. Then we need to create an entanglement like the GZ state here. The sensing part is the fastest one, if you want, especially in our scheme where we just apply a spin echo on all the spin and sort of apply this phase rotation to check that indeed we were creating our GZ state. And finally, as I mentioned, we need to indeed perform some decoding to map the information which was on the 3-spin only on the MV center to extract the information about what we are trying to sense. So as you can see, even if the coherence time were not reduced, which is actually indeed is, only just this practical aspect of operating with entanglement make it very difficult if you want to actually achieve an enhancement in sensing. So what can we do? Well, we wanted to at least try to evaluate if this entanglement and sensing can give us some advantage. And so instead of actually looking at the 3 GZ spin state, we try to characterize a bit more carefully just using 2 entangled spin, just because the experiment is a bit simpler and allows us to make a much more precise calibration of the system. And so here what I show is how my signal changes when I vary an external field, the magnetic external field amplitude. And so the signal that I observe will sort of oscillate depending on the external field and can extract from this oscillation the amplitude of the field itself. And so here I can compare what is the oscillation when I use 2 entangled spin and when I use 1 single spin. As you can see, the oscillation for the 2 entangled spins are twice as fast. And so this is good. It tells us, yes, I'm creating, in this case, a Bell state. And so I can indeed achieve, if you want, an enhancement of the phase acquisition due to the entanglement. However, if we look a bit more carefully at the slope here around this 0 point, the slope for the 2 experiments are pretty much the same. We just shifted the phase so that they were not exactly on top of each other. But the slope indeed looks very similar. So what is going on? Well, the contrast for the single spin is much larger, about twice, than the contrast for the 2-spin entanglement. And this is due to the fact that we have some control errors, so overheads, as I mentioned, in our initialization and control and creation of the entanglement. And we also have some additional decoherence of the entangled spin with respect to the single spin. And so in all, this sort of tell us that, well, considering that the noise in the readout is more or less the same because I only measure just at the MV center, I don't really have an advantage here by using 2 entangled spin with respect to a single spin. So this was, of course, a bit disappointing for us because we were hoping to find at least some regime where indeed using some entanglement would help us. But in hindsight, is of course not so surprising because a lot of people have been telling for a long time that indeed reaching an enhancement with entanglement in sensing is not so easy. So what is then that we can try to do? Well, we can try to think about a different paradigm for exploiting entanglement in order to improve quantum sensing. So as I said, there is 2 categories that we are really interested in for quantum sensors. So one is just to use some simple quantum property if you want coherence, and 2 is actually to use quantum entanglement. But maybe there is some gray area in between these 2 that we can try to populate. So instead of trying to use entanglement in terms of massive entanglement between many quantum sensors, we can try to use a composite quantum system, which might or even might not display some strong entanglement, maybe just like some type of coherence like discord. But in this case, we want to achieve a task that a single qubit sensor cannot actually achieve. And so it's a category in between, which might give some practical advantage on the near term, instead of waiting to have very good control on large entangled system, which we still hope to achieve someday in the future. So what are the type of things that I have in mind here? So there are many different challenges that one want to solve to improve single spin sensors. For example, like I, of course, always think about MV centers, but these are somehow similar to other systems. You might have an inefficient readout of your spin sensor. And so one strategy that has been proposed is to perform repetitive readout using an ancillary qubit as a memory. You might be far away from the target that you want to measure, and so you might use an additional qubit to sort of bridge the gap between your sensor and the target. It might be difficult to measure transverse field, and so I will show you some ideas of using an ancilla to also perform frequency up conversion. A big challenge is, of course, coherence time, and so you might use additional qubit either as a memory or maybe to even implement some quantum error correction. Then finally, you can bring that idea even forward to perform feedback, or even sort of modify this idea of using a reporter spin to actually use it as a transduction mechanism to transform some chemical or biological signal into magnetic and electric field that your typical sensor are more easily able to actually measure. So this is indeed the strategy that we pursued. So the first example that I mentioned is to implement a repeated readout. So we had this MV center coupled to two electronic spin nearby. And so we actually exploited the one spin, spin one, to create this bell state, which was giving us some advantage, but not enough to actually beat the performance of a single spin. But now, after having created the entangled state, instead of just mapping information to the MV, we can also exploit this second electronic spin as a memory, since it's stable under optical illumination, to preserve the information about the measured signal, and then feed it back to the MV center over many multiple readout cycle, optical readout cycle of the MV center, to enhance the signal itself. So this has been done before using the nuclear spin of the MV centers, but here the advantage is that since we already have this additional ancillary system, we have a relatively strong coupling between the two. And also the fact that we have initially an entangled state between the two, we sort of save some time, but not having to transfer that onto the nuclear spin itself. And indeed, we see that we can increase the contrast in our signal when we perform from 0 to up to n repeated readout. And this finally allows us to achieve some enhancement over the performance of just using a single electronic spin, the MV centers, to perform sensing. It's still not an enhancement that is so large that it's sort of like game-changing, but I think as a demonstration of the principle of trying to exploit additional spins, not just for entanglement, but to perform different tasks, this is a powerful demonstration, because it really allows you to show that if you think out of the box to try to find new ways to exploit what nature gives us, you can indeed achieve some improvement. As I said, there are quite a few other ideas that you can think of in order to exploit a small number of ancillary qubits to enhance sensing. So one that we worked on was the idea of using the ancilla qubit in order to perform frequency up conversion. And really, this ancilla qubit now works as a quantum lock-in amplifier. So this has already been discussed, for example, by Amir Jacobi, that we can use dynamical decoupling, a series of pi pulses, in order to refocus a quasi-static noise, here in purple, and still be able to detect some AC fields, some oscillating fields. And the key idea is that these pulses will decouple noise, which is lower than the action of the pulses themselves, while we can select a particular frequency that we let pass through. And so these pulse sequences, in some sense, perform as filters. The problem is that, of course, many fields that we might be interested in are actually not at the high hundred of kilohertz to megahertz frequency that this schemes is particularly good at, but are instead at the low hertz to almost static frequency field, frequency range. And so we might want to have some different scheme in order to be able to also detect a quasi-static field. So what can we try to do in order to sort of achieve the advantages given by dynamical decoupling, but for DC fields? Well, the idea is to sort of think about an instrument which is very common in labs, which is the lock-in amplifier. The idea is that you have a signal which is indeed static, and you mix it with a reference that you have in control of, and this allows to sort of upconvert the frequency of the signal to a higher frequency where the noise is less. Then you use a bandpass filter to select only frequency around your reference frequency here. And this allows for noise, like a reduction in noise in your detection. The problem is that, of course, these instruments are typically, if you want, large. And so what we wanted to do was to find a way to sort of miniaturize the lock-in amplifier with respect to the MV center entanglement. And indeed, what we have is that we have an intrinsic reference field, which is given by the nitrogen nuclear spin associated with the MV center. Especially the nitrogen 14 has its own intrinsic frequency given by the quadrupolar resonance frequency. And so what we can do is indeed to sort of exploit that spin there. This allows to upconvert the transverse magnetic field frequency from static to the frequency of the nuclear spin itself. And then we can apply dynamical decoupling sequences to filter out only the signal oscillating at the upconverted frequency. And this allows for much longer coherence time because we are erasing noise from other sources. In addition, we can combine conventional Ramsey sensing, which is the typical way that you would detect DC fields, plus this ancillary upconversion technique in order to measure both transverse field and longitudinal field. We achieve more or less the same sensitivity with the two methods. And so we are able now to have a miniaturized vector magnetometer, which only really require one single NV centers. And so it can operate with very high spatial resolution. So the addition of an ancillary qubit, the nuclear spin, allows us to do something which was not possible without it, to achieve this vector magnetometry, or even more simply, just the detection of static transverse fields. So another example of what one can do if you have some additional spin qubits that you can use close to your sensor, some additional qubits more generally, is quantum error correction. And the idea is quite simple. It's very similar to error correction that you might have in quantum computing. So instead of having a long evolution time during which your sensor is acquiring some phase, you interrupt that and only acquire it at some point. And in between, you apply some recovery and correction operation that allows you to detect the error and recover this data in an error-free way. Of course, the question is, can we actually implement error correction and do sensing at the same time? After all, what we are trying to sense is unknown, and so it could be a thought of as some type of noise, but the error correction itself is canceled. So this is sort of, if you want, a compromise between sensing and quantum error correction. Indeed, one of the first examples was based on the GS state that I talked about before, and this seemed to give you the best possible of two worlds. So you get an Heisenberg limit in the phase estimation because of this n times or 3 times enhancement of your phase. You're also protecting your system against bit flip noise, something like sigma x error. However, unfortunately, you are not protecting against dephasing. And your effective T2 is indeed 1/3 shorter than it was for a non-entangled state. So really, you typically will not have a signal-to-noise ratio improvement if you also have dephasing. And so there has been, after this early work, some works which were trying to state some formal requirement for error-corrected quantum sensing to be possible. And the idea, although expressed in a very mathematical form in this paper, can be sort of pictorially represented in the following way. So if you have your signal represented in one direction and your noise represented by another arrow, if they're perpendicular to each other, well, yeah, you will have a code. But if I have some overlap, then a code for error correction and sensing does not really exist. So this seems to sort of limit a lot of what you can do for error correction and sensing. There was another caveat, which was that these schemes required noiseless ancillars, which is typically not very practical. But the two most important problems to me was the following. So first of all, there is always some noise associated with the signal that you're trying to sense. And so, yes, there's always going to be a component of your noise around the signal direction. Also, well, if your sensor is very noisy or very sensitive to the noise in one direction, that's the direction where you would like to try to measure things, because it means that your sensor is particularly sensitive to fields in that direction. And so you're using your sensor in a not optimal way. So we came up with another different ideas to try to find a different compromise between sensing and error correction. So we are seeing that dynamical decoupling exploits temporal correlation in the noise, which are different from the temporal correlation in your signal. So the frequency of your signal is different than the noise typical frequency. A second way to distinguish noise and signal is to use a different algebraic coupling. The noise is along Z, and the signal is along X, for example. Finally, what we proposed was to actually use spatial correlation in your noise in order to distinguish it from the signal and achieve error-corrected quantum sensing. So I feel that I'm almost out of time, so I'll try to accelerate and just give you the flavor of this. But the idea is that indeed, let's say that you have your 3 qubits that you want to use in a error correction codes. Each one of them will feel different noise with different spatial correlation, and instead your signal is uniform. Then, similar to dynamical decoupling, you can filter out your signal from the background of the noise. And in this way, we can actually achieve some improvement in the sensitivity using indeed the error correction quantum sensing with respect to just not doing anything. Of course, sensitivity is better when it becomes low. So I want to conclude here and sort of like leave you with a message that indeed there is always this compromise for quantum sensor between trying to achieve a very strong coupling to the signal of interest and isolated it from the environment. And so there are a lot of things that having a few ancillary qubits can give you. So for example, you can achieve improvement by using quantum error correction as long as there is some difference between your signal and your noise, and that difference can be indeed in spatial correlation. More generally, even beyond trying to achieve the Heisenberg limit, even some small amounts of entanglement can indeed achieve tasks which are not possible using single or unentangled qubits. So before concluding, I want to at least acknowledge the people who have actually done the work. So the first part on identifying novel qubits in diamond and then exploiting them for sensing was done by Alex Cooper, who's now in Waterloo, together with Calvin Sun, who's continuing that work now. The part about achieving upconverted detection of transverse field was done by Ishan Liu together with Ashoka Joy, who's now at Berkeley. And David Leyden led the effort for quantum error correction, and he's also moved on and is now at IBM. As you can see, I have a lot of people who have left, so if anybody's interested in a postdoc or even joining for PhD, if there are undergrad students here, please do contact me. I'll leave up the conclusion and outlook, and I'm happy to answer any questions.
So, Paola, thanks very much for a fantastic talk. It's great to see how entanglement can really enhance sensitivities and bring new things. Friedemann, I'm going to hand over to you for a selection of questions. You're still on mute, Friedemann.
Sorry, we do have some questions. Maybe we start with that one. Can the vector magnetometer be realized with NV ensembles, or does it require a single NV?
Oh, that's a very easy one. Yes, you can do ensemble, and I presented only single NV in this talk, but we do have a lot of work both in my group and many other works and other groups around the world exploiting ensembles. Typically, like when I mention ensembles, the ensembles are not entangled indeed. Like it would be nice, and there are people working on in trying to entangle large and dense ensemble of NV centers. It is quite challenging, but I think that I'm sort of hopeful that we will see at least the ability to create a large entanglement. Again, if that leads to an improvement in the sensing, that's even more challenging. But I think that both questions are very much interesting, both just creating entanglement and then trying to exploit it.
Okay. There is one more question, which is, well, this is a very general one. Is it true that more entanglement means more sensitivity, or do you need the right type of it?
No, so like like more entanglement doesn't mean more sensitivity. Typically, indeed, you get, if you want less sensitivity, if you don't do things carefully. So like in this prototypical example that I showed about if you wanted the GSE sensing, what like it can be calculated. Let's see if I can find it again. What you can actually calculate is that indeed you will have an enhancement of square root of n in the sensitivity. Oops, I should share screen again. But as soon as you add noise, this interrogation time here becomes typically n times shorter, because your noise is, your coherence time is also n times shorter. So the optimal point of sensing is sort of like equivalent for either using n unentangled spin or n entangled spin. This, of course, assume this particular type of entanglement, a particular type of noise model, and so on and so forth. So there is wiggle room to indeed find some type of entanglements which might be more robust. Sometimes you might not be indeed limited by the coherence time of your sensor, but by the coherence time or the stability of your target, and so maybe decoherence is not a problem. You could try to use things which are not a cut state. You could try to use different type of entanglement which give different compromise. The noise model might not be so bad. So if you have a correlated type of noise model, the coherence time is not simply n time shorter. So there is a lot of wiggle room, which I think it's very fascinating to explore, and it might give indeed a final advantage. As I said, in all of these, you also had to factor in, if you want, overheads due to preparing your state and reading it out. And when you're considering, again, if you wanted the signal to noise ratio per unit time, these are also quite important. So what was, in our experiment, what was killing us was that it really takes us a long time to prepare the state, because we need to sort of cool down the additional spin using the NV center. So we have a limited source of sink of entropy, if you want. And so it's very difficult to achieve an advantage. Other system might be better.
Okay. So I think we are close to the time that we allotted to questions. So maybe it's time to move on and shift all the remaining questions. There are a couple of them into the panel session.